like what was it called? Sine functions.
But you're in trig now.
Yeah. We just got into trig.
Just started. So, okay.
Yeah.
So
right now we're working on like inverse tangent, inverse cosine, and all that stuff.
Okay.
But I have a test that I am doing test corrections on to get just like some more credit for, and that's like the most pressing of my issues right now.
Can you verbalize some problems, and I'll write them, and then we can talk about them?
Yeah. Okay. So I'm pretty sure. Wait, let me find the pen. Sorry. Okay. I'm still viewing your screen, and I don't think I can edit the drawing pad.
That's correct. You're going to be looking. We're both going to be looking at my screen. But if
okay.
verbalize the problem, I'll write it, and then we'll both be able to work on it.
Okay. So the first question I have about is just a parabola problem.
Okay.
I'm supposed to find the vertex, directrix, and focus. Sorry.
Okay. Uh-huh.
And the equation. What was that?
Yeah, go ahead. Yeah.
Okay. And the equation is y squared minus 6y minus 2x equals 0. So I've gotten to the step where I have y minus 3 squared minus 2x plus 9.
Okay.
Yeah, but I'm just kind of confused. I'm like, do I factor out the 2 out of that equation, making it 2x plus 4.5?
Well,
is that right?
Let's move the 2x to the other side.
Right.
And then you're correct. You complete the square.
Mm-hmm.
What did I have to add? 9?
Yep.
So let's also subtract 9.
Wait, why is that?
Well,
sorry.
When I completed the square, I added 9 to the left side of the equation.
Right.
So if I subtract 9, I've got the same thing now. In other words, this is the same as that.
Okay, but is the minus 9? I guess I've never done it this way, so I'm like a little bit confused by it.
The only reason I left the 9 on that side is because what we want to end up with is 4px equals a times y minus some h squared plus k.
Okay.
Okay? And the vertex will be h and k, and the directrix will be p away from the vertex, and the focus will be p away from the vertex also. Okay?
Yeah.
So our goal is to get it into this format. So that's why I want the 9 over there.
Okay.
Okay? So now, if I let that equal to 2x, I've essentially got it in vertex format.
Okay.
Okay? So I can say the vertex, hold on a moment. Let me think about this for a second. When you work on parabolas, do they use 4p? In other words, is this your standard 4px equal y?
But it's not in that format. It's basically like the format that we've been using. Our teacher, Mr. Slaughter, he kind of despises the way the book does it a little bit.
So he does it this way. He does it x equals a times y minus h squared plus k, and then go ahead. And then to figure out p, a is equal to 1 over 4p.
Not really.
Okay. How does your teacher do it?
Here, let me find the equation for it, because I know I have it lying around somewhere, but I just it doesn't look familiar. Maybe he just used a different variable and that's thrown me off.
Well, you know, the school systems in Colorado do it two different ways on these parabolas.
Yeah.
And it's always annoyed me a little bit because, gosh, you'd think they could get their act together and just do it the same way.
Okay, so the format he's using is either x minus h squared is equal to 4p y minus k, or y minus k squared is equal to 4p x minus h.
So, say again, 4py equals...
Minus... No, it should be 4p y minus k, and the y minus k is in parentheses. And... yeah, and then he has the squared term next to it, x minus h squared, and he's basically like...
Okay, I got you.
Yeah.
Okay, and this doesn't fit ours because we have an x and a y squared. So the one we're looking for is 4p x minus h
squared.
That's equal to y minus k squared.
Oh, yeah, y minus k squared. Okay. Yeah, that makes sense.
All right. So that's what we're looking to put it into. And if we can get it into this format, then we know our vertex is at hk, h comma k, and we know that our focus length is p. So how do I get it into this format? Well, we'll add the 9 to the other side.
Okay.
Now we've got this in this format.
Yeah.
So all I got to do is factor out a 2.
Right. Yeah.
And I end up with 2 times x plus 4.5 equals...
Making the vertex...
Yes.
3 negative. Okay.
3 negative
All right, so
4.5. And it makes, now you can equate 4p to 2. So 4p equals 2, making p equal 1/2.
Okay.
Okay? And
yeah, well that clears up.
yeah, in terms of graphing that, we were at minus 3 minus 4.5. Right here is the vertex. It's a horizontal parabola, not a vertical parabola. Whoops. In other words, whenever you have it y squared and x, those are horizontal parabolas. And we know it's going to open to the right. So it's going to look something like this.
How do we know it's going to open to the right?
Because that coefficient is positive on the y squared.
Oh, okay. All right.
Remember, parabolas are interesting because they kind of teach them in two different ways. They start off teaching you it as a quadratic. And this is what annoys me a little bit, is they start off this format here. And they'll even put it in vertex format, which is this. And then when they teach you parabolas as conic sections, which is where you're at now, they give you a different format. They give you this 4p there and take away the a. And most people find that quite confusing. They do it because it allows you to calculate the focus much easier by using the 4p format. So if I know my vertex is there and it opens to the right, then my focus is 1/2 to the right of there, and my directrix is 1/2 to the left of there. The focus is always inside the parabola. The directrix is always on the other side of the vertex. And these two distances are the same, and they are both p.
Right. All right. Well, that's kind of what I needed on that problem. Was all that. The next problem is I'm kind of just like forgetting how to determine the difference between an ellipse and a hyperbola. So the problem reads, write the equation for a conic section whose center is 3, -2, vertices at 3, 4, and 3, -8, distance from center to focus of 8, and this is the part that kind of hangs me up here, is that it fulfills the requirement that the distance between the distances to the foci of any point on the graph is a constant.
Okay.
So,
You went through those a little quick.
oh, yes, sorry.
What were they again? 3 comma minus 2 was the center?
That was the center, and the vertices were 3, 4, and 3, -8.
And this is an ellipse?
Yeah.
Okay. So let's...
And the distance...
Yeah.
No, this is...
Let's figure out whether it's horizontal or vertical, because that'll affect the general formula that we're going to use. Okay?
And I don't have to graph it. So.
Well, even if we don't have to graph it, it'll be useful because it tells us, in other words, by knowing that my major vertices vary in the y-coordinate only, in other words, one of those vertices is there, and the other one is down here, that tells me that it is a vertical ellipse.
Okay.
And the general formula for a vertical ellipse is, well, the general formula for a horizontal ellipse is x minus h squared over a squared plus y minus k squared over b squared, and all that's equal to 1. Okay?
Yep,
that's horizontal. If it's vertical, then the a squared goes under the y minus k.
Mm-hmm.
Since this is vertical,
So,
that's what I'm going to do, is I'm going to put that as b squared there and the a squared there. Now,
so I got that.
So a is this distance, b is that distance.
Mm.
Okay, so according to our major vertices, what is a?
6.
Okay. And
So there's that.
they didn't give us the minor vertices. What else? What other information did they give us?
The distance from center to focus is 8.
Okay. So there's a focus and there's a focus. So they're saying this distance here is 8, and that is C. Okay?
Yeah.
You actually have 3 variables. You have an A, a B, and a C.
And this is where I get hung up on the difference for this equation for the hyperbola and ellipse is the a squared plus b squared is equal to c squared or the a squared minus b squared.
For a hyperbola, remember it's the Pythagorean theorem. It's c squared equals a squared plus b squared.
So this is going to be the...
An ellipse, it's b squared minus a squared. Excuse me, it's a squared minus b squared.
Right.
Okay, and that's important because if you solve for c, it is the square root of a squared minus b squared, and that tells you that a always has to be bigger than b. So if you find yourself with an a smaller than b, you got it backwards.
Okay.
What did they give us for the distance? 8. So I can plug in 8 for c. I'm trying to calculate b. So a is 6.
And then minus x or b, whatever.
So if I square both sides...
28, right? Oh, wait, no. Oh, okay. See, Well, you'd have to minus a negative, right?
Well, hold on. I've done something wrong here. C was 8. There's no way C can be 8 and A can be 6. Notice that A is the distance from the center to the vertice, and from the center to C is always smaller. So C is always going to be a smaller number than A for an ellipse.
Okay, so I guess the equation is undefined.
Well, no, it's impossible. This might be a hyperbola. Do we know, I mean, yeah, do we know if this is an ellipse or a hyperbola?
No, we don't. I just...
Sounds like it's a hyperbola. In other words, the fact that we have a greater than, or the fact that we have a C greater than A, you can't have that with an ellipse. However, you can have it with a hyperbola.
Is there any way to kind of tell off the bat besides that? Or
Usually they tell you. I don't see too many problems where they don't tell you whether it's an ellipse or a hyperbola. And that's why I assumed it was an ellipse. You usually start out with ellipses. But the difference between hyperbolas and ellipses is hyperbolas, there is no constraints. We have this imaginary square in the middle, and A is always the distance measured along the major transverse axis, and B is always this measurement. And the dimensions on this rectangle, rather, can be anything. In other words, A can be smaller than B, A can be greater than B. But also notice the focus. This is C, from here to here, bigger than A, always.
yeah.
So, really, the moment we found out that the distance to the focus was 8 and that the distance to the vertice was 6, that means it's a hyperbola. I didn't notice it at first. It's been a while since I worked with this conic section. But that's what it's going to mean, is that we're dealing with a hyperbola, not an ellipse. Okay? So, what does that mean? That means that the equation is not c squared equals a squared minus b squared. It's c squared equals a squared plus b squared.
Okay.
Okay? And it still means that we're dealing with a vertical hyperbola.
Okay.
Okay? And that's going to be significant also. In other words, we're not dealing with the hyperbola like this. We're dealing with a hyperbola like that. And the difference is this one is y squared, if it's at the center, it's y squared over a squared minus x squared over b squared. Whereas if I had a horizontal, it's x squared over a squared minus y squared over b squared.
And it's always going to be minus for hyperbolas?
Yes. It's always a minus.
Is it any different?
The only difference is whether the y is first or the x is first.
And is the sign in the middle any different for ellipses or no?
Yes, it's always plus.
Oh, okay.
Okay?
Quite a bit.
So if you have an x squared plus y squared, you're dealing with an ellipse. If you have either an x squared minus y squared or a y squared minus x squared, you're dealing with a hyperbola.
Okay.
And this is a horizontal hyperbola, and this is a vertical hyperbola, this being vertical. Okay?
Yeah.
And, of course, if it's vertical, A is always measured on the line that connects the two vertices. In other words, the straight line that connects that vertice with that vertice, that's where A is always measured on. So A goes under whatever variable that is. In other words, if it's a vertical hyperbola, A has to go under the y squared term. If it's a horizontal hyperbola, then A goes under the x squared term.
All right.
Now, the fact that you gave me the vertices were, here, let me redraw it as a hyperbola instead of an ellipse. Just so I can get a feel for it. Let's see. It was 3, 4 and 3, -8, right?
Yep.
So we must be dealing with something that looks like this. A vertical hyperbola this measurement was 6. The center, what was the center again? It was 3 comma 2?
3 comma negative 2.
3 comma negative 2. Good. I'm on the right side of the axis. And the distance to the focus was 8. So this distance here is 2. And we can figure out b, because we know that c squared equals a squared plus b squared. Well, c is 8, so we have 64 equals 36 plus b squared. B is going to be the square root of 28, which is 2 root 7.
Okay.
So I have my equation. I know it's going to start y minus y plus 2 squared all over 36 minus x minus 3 squared all over 28 all equals 1.
Okay, so I guess my question is, does the one with the a value always have to come first, or does it matter? Like, in this case, does y squared have to come first, or could the x squared come first?
No, y squared has to come first. In other words, if you get a polynomial and they want to know what kind of polynomial it is, in other words, let's say they give you a complicated polynomial, and you're looking at terms like this. That means it's a vertical hyperbola. If you're looking at terms like this, that means it's a horizontal hyperbola. If you're looking at x squared plus y squared, it's an ellipse. If you're looking at y squared plus x squared, it's an ellipse. If you're looking at minus x squared minus y squared, that's also an ellipse, because I can divide both by minus 1. To end up with x squared plus y squared. So it's only if they have opposite signs that it's a hyperbola, and whichever variable has the positive sign, that goes first and goes over the a squared. So basically they're going to give you 2 out of these 3 variables, which they did. They gave us, well, they gave us h and k when they gave us the center. And then they gave us a by giving us the distance between the 2 vertices. And they gave us c, which allowed us to solve for b. So if you can come up with a, b, and c, actually you only really need to come up with a, b, h, and k. But c you have to come up with frequently in order to come up with the a or b. In other words, they'll give you the c. It's rare that they give you A, M, B, H, and K. There's no calculations that are needed if they give you all of those.
Okay, so my final question was on a word problem. This was the last question on the test.
Okay.
This was like a pretty in-depth word problem, so it might take me a while. Or take you, I don't know. A whispering room is one with elliptically arched ceilings. If someone stands at one focus of the ellipse and whispers something to his friend, the dispersed sound waves are reflected by the ceiling and concentrated at the other focus, allowing people across the room to clearly hear what he said. So suppose such a gallery has a ceiling reaching 20 feet above the 5-foot-high vertical walls at its tallest point. So, and that bit of information, I was kind of like, do the 5-foot vertical walls really matter?
I'm trying to picture this thing. Okay, so the picture I've drawn is from the ground up, right? In other words, you're standing in the middle of the floor and you look up, you see this elliptical ceiling. Is that, do I have it right?
Yeah, it sounds right to me.
Well, okay. The thing about ellipses is they have a really magical property, that any straight line that's fired at the edge bounces off precisely so that it'll go to the other focus. No matter where. In other words, if I fire a ray right there, let's say we had a table shaped like an ellipse, and I had a bunch of tennis balls. And I rolled the tennis ball in this direction, it's always going to rebound towards the other focus.
Is that possible in life? I mean,
yeah, no. This is the way telescopes are designed, and flashlights. Flashlights use parabolas, and parabolas have a similar impressive property. Here, let's just talk about a parabola for a second, because you can relate to it a little bit easier, because they make flashlights out of parabolas. Why? Because they can put the bulb right there, and any piece of light gets bounced off vertically no matter where it hits. If I aim a piece of light there, it goes off vertically. So the flashlight takes all of this light that emanates from the bulb and directs it to go vertically out. It's also the way telescopes take in the light from distant stars and focus it to the focus. In other words, with a parabola, any light coming in, you got a star that's 100 million miles away, well, that light comes in, hits that part of the parabola, and gets reflected to the focus. Light over here coming in hits that part and gets reflected to the focus. So no matter where the light comes in, it gets received there. That's how all telescopes work, and flashlights. And ellipses are a little different property, but basically the same, in that they use ellipses to break up gallstones in people. And the way they do it is they have their sound creating device right there. They cut away half of the ellipse so that you're only looking at this much of it. The sound wave bounces off of all sides of the ellipse at once, but every single one is directed towards your gallstone. The little person sitting in a chair right here, and they turn on the sound machine, and it proceeds to break up the gallstones, because all of the sound is redirected to that second focus point in the ellipse. In other words, if I drew the full ellipse, it would be like that. So the sound comes out in 360-degree direction from the first focus, but every bit of it gets focused towards the other focus.
Oh.
Hyperbolas have a similar property. If I had a pool table shaped like this, there's the two foci of my hyperbola, and I'm over here and I shoot a tennis ball towards that focus, it bounces off and goes that direction. If I shoot, hold on.
Okay.
Yeah, no, that's right. Because those things, in other words, if I shoot the tennis ball there, it bounces off in that same direction. So parabolas, ellipses, and hyperbolas all have these reflective properties that make them wonderful for building flashlights, telescopes, mirrors. A telescope frequently will have all three in it. It'll have a parabola to redirect the light that's coming from the stars, and then it'll have an ellipse inside to take that light that's already been focused on a single point and reflect it to the other focus point of the ellipse. And then it uses hyperbolas also at some point in the telescope. But they're all based on these reflective properties. So, back to your problem of the room with the elliptical ceiling. Now, let me just draw a side view of that also. So here we have our elliptical ceiling, and you're saying the sides of the room are 5 feet high.
Yeah.
And that people standing down here, so if this guy whispers, this guy can hear it.
So they're the two foci, right?
Right.
Okay.
The only thing that I don't get, I mean, I certainly get the fact that see, they're not really at the foci are up here on the ceiling.
Mm.
So if they were to climb up this 5-foot wall and say something, then sure, all of those sound waves, no matter how soft, are going to reach the other foci. So the question is, what is adding the third dimension do to this problem? And
I don't think he meant to have a third dimension. This is like the way he said it was just basically just like a basic ellipse problem.
Okay.
So I'm guessing he meant the foci to be within the
okay.
ellipse.
And so what's he asking for? What's the problem asking?
It just asks him to write an equation, and also this is the part I got hung up on, is tell me the height of the ceiling above each whispering point.
I think I have my picture wrong here. The ceiling is elliptical?
Yes. I just kind of like thought the ceiling as being like just like a half ellipse, I guess. That's what I thought it meant.
Ah, I did have my picture wrong. So the ceiling is like that. Now I get it. And here's your walls. They're 5 feet.
And that's why I was kind of like, do the walls even matter?
Well, and so one person is standing there, and if I had the other half of the ellipse, the other person's standing there. And even if I don't have the bottom half of the ellipse, in other words, even if my room is like that, it still means that if this person whispers, it gets reflected to the other foci. In other words, it bounces off the ceiling. Even if he aims at the ceiling and talks at the ceiling, that thing bounces there and goes directly to the other foci.
Right.
So, now, the 5 foot. That tells us that there's 5 feet between the foci. Right? In other words, the center of the ellipse has to be there. If I had the full ellipse, in other words, if the ground was also elliptical, it's not. It's going to be a hardwood floor, but presumably below that, like that. And also, if this person whispers, you're not going to bounce off the walls because they're not elliptical. But maybe he meant them to be elliptical. I bet he did. I'll bet you this problem is this. Oh, let me draw a vertical ellipse. That'll work better. So this is the ceiling part. One person's there, the other person's there. So the whole room, see, this whole problem would make a whole lot more sense to me if you said the walls of this room were in the shape of an ellipse. In other words, the
Yeah,
perimeter of the room is an ellipse. Now, if you had two people standing, then anything they said would immediately get focused on the other foci.
I guess I just kind of, because I ended up drawing this problem like really different, and he seemed to think it was right. I wish I could show you what I drew because it's kind of hard to describe. But I guess I'll try and describe what I have to you.
Okay.
So basically, it's just like it'd be one piece of a horizontal ellipse, and
as the ceiling,
he says
like that.
Yeah, and I kind of just the 5-foot walls really to me like didn't make any sense at all. Like they were just there to distract me because it says
Well, the question is do you have two people here and there?
Yeah, I think so. That's
Okay.
what I do.
That's the right picture? All right. Well,
I believe
the 5-foot ceiling might make some sense then. Because if you have the two people there, and it's 5 feet to get to there, that tells me what B is. That tells me B is 5 feet. Does it say how far the two people are separated by?
No, it just says, suppose a gallery has a ceiling reaching 20 feet above the 5-foot vertical walls at its tallest point, and suppose the foci of the ellipse are 30 feet apart. So it does tell you how far the people are apart.
Okay, so that's 30. The highest point is 5 feet, so that's 5.
Ooh. I think he actually meant like okay, so the very left and very right edge of the ellipse, I just think he meant like the 5-foot walls came down from there, and then from the ground level of these people, it was 20 feet from them to the top of the ceiling.
Okay, so we had a 5 also? It's
No,
what?
it was...
So it seems to me like
Do you want me to just read you the whole...
well, it seems like we have 3 measurements. We have a 30, which half of that would be C. So C would be 15.
Right.
We have, I think we have a B. Oh, maybe we just have a B, and we have to calculate A.
Yeah, I think we actually had a B and a C, and then we had to calculate A.
Yeah, so our equation is going to be x squared plus y squared, x squared over a squared plus y squared over b squared equals 1.
Yeah.
And now the question is, what numbers do we have in our possession here? And we know that c squared equals a squared minus b squared. So the question is, c is clearly 15, because the people are separated by 30, and the distance from the center of the ellipse to the foci is c.
Okay.
So my only question would be, what is this 5 feet? Is that B or is that A?
To me, that's irrelevant because it just says that those little vertical walls at the ends of the ellipse, those are 5 feet, and then from the people to the top of the ceiling is 20 feet.
Ah, that's why you think it's irrelevant. I think you might be right. In other words, if my picture is right, 20 is B, right?
Yes.
Yeah, 20 is B. Okay, and yeah, I agree with you. I think that 5 foot, I don't see how that matters because once I have a C and a B, I can now calculate A. Once I have A, I have my equation.
Right.
So C squared would be 225 equals A squared minus 400. So A is 25, right? Square root of 625 is 25. And now we have our equation. X squared over 625 plus y squared over 400 equals 1.
Yep. And then the second part of the equation was, tell me the height of the ceiling above each foci. and I had like no idea how to do that at all.
So this distance here.
Yeah.
Okay. Well, we have an equation of the ellipse. So every point on the outside of that ellipse has to fit this equation.
Okay.
Okay. So my y value when x is 15 is going to be the height of that ceiling.
Okay. Oh, so we just plug 15 into the equation and then solve?
Solve for y.
Oh, okay.
Notice that if I start at here, my x is 0. In other words, if I put a coordinate system on this thing, like that, and I want to make sure that that height is 20, well, if I put in 0 for x, which is what x is right there, I'm going to figure out that y is 20. So if I put in negative 25 for x, I'm going to find out that y is whatever, it's 0. In other words, the height over here would be 0. A person wouldn't even be able to stand over there. But they can stand here. There's enough room for them to stand, or, yeah, there's enough room for them to still have room above their head. Yeah, and this kind of makes sense also. Your picture makes sense because if they talk, not only does the sound travel directly to the other person's ear, but it also bounces off the ceiling and goes there. So even a whisper would be able to be heard. It only bounces off of one half of the ellipse. It doesn't bounce off the bottom half because there is no bottom half. But the key is once you have the equation of the ellipse, then every point on that ellipse has to agree with that equation. So if my equation is x squared over 625 plus y squared over 400 equals 1, then this point here has to satisfy that, this point here has to satisfy it, no matter where I'm at has to satisfy, the x and the y values have to satisfy this equation. That's what the equation basically means. And it's only on the circumference of the ellipse that that's true. So if you were trying to figure, if you knew the foci was there, or maybe here, and I want to know what this distance is, well, what is that? That's the y-coordinate of that thing right there. And the x-coordinate we know. We know the x-coordinate is minus 15. So whatever the y-coordinate is the height of the ceiling over their heads. Okay. I'm going to have to run. Usually these initial sessions are only half-hour sessions, and I've gone over a little bit. Unfortunately, I have another session I have to get to, so I can't continue any longer. But I hope... Oh,
that's fine. That was my last question.
Good, good. Certainly, if you have any questions with the trig, I can certainly be helpful there also. Trig's my favorite project to tutor, actually.
Cool. Yeah, you were a big help. Thanks for your help on this.
And let's see. Let me just give you one more piece of information.
Okay.
If you decide you want another session, go to this website. It's a little smoother. It's Digital Math Tutor. This is also my website, but it's probably, the one your mom probably went to was probably algebra-to-calculus.com. Algebra-to-calculus-tutor.com. If you go to this one, it's a little easier to schedule sessions and pay. This has a real smooth payment system built in, PayPal. There's no charge for this session, but future.
Oh, thank you.
future sessions there would. Yeah, no, I offer a half-hour session for free to everybody. So, okay, Brent, nice working with you. I hope to talk to you again.
Okay. Yeah, you too.
All right, bye-bye.
Yeah.